Hello everyone! Welcome to the e-learning course Unix for QC. In this module, we will introduce you to architecture of Unix OS. We will talk about kernel, processes, memory, and file management. The kernel is the essential center of a computer operating system, the core that provides basic services for all other parts of the operating system. The kernel of Unix is the hub of the operating system. It allocates time and memory to programs and handles the file store and communications in response to system calls. The kernel is the first part of the operating system to load into memory during booting, and it remains there for the entire duration of the computer. Thus, it is important for it to be as small as possible, while still providing all the essential services needed by the other parts of the operating system and by the various application programs. The kernel provides basic services for all other parts of the operating system, typically including memory management, process management, file management, and I/O input-output management, that is, accessing the peripheral devices. These services are requested by other parts of the operating system or by application programs through a specific set of program interfaces referred to as system calls. If you need to check which kernel version your server is currently running, use the following command, uname-r. You should receive a result similar to the following. Output can be interpreted with the following key. Whenever you issue a command in Unix, it creates or starts a new process. A process, in simple terms, is an instance of a running program. The operating system tracks processes through a 5-digit ID number known as the PID or process ID. Each process in the system has a unique PID. The kernel keeps track of all these processes and stores a little bit of basic metadata about them in a process table. In Unix, it's possible to have multiple processes for the same program. When you start a process, run a command, there are two ways you can run it: foreground processes and background processes. Foreground processes. By default, every process that you start runs in the foreground. While a program is running in foreground and taking much time, we cannot run any other commands because prompt would not be available until program finishes its processing and comes out. In other words, foreground processes run on the screen and need input from the user. Background processes. A background process runs without being connected to your keyboard. If the background process requires any keyboard input, it waits. The advantage of running a process in the background is that you can run other commands. You do not have to wait until it completes to start another. Parent and child processes. Each Unix process has two ID numbers assigned to it: process ID, PID, and parent process ID, ppid. Each user process in the system has a parent process. Most of the commands that you run have the shell as their parents. Zombie and orphan processes. Normally, when the child process is killed, the parent can do some other task or restart a new child as needed. However, sometimes the parent process is killed before its child is killed. In this case, the parent of all processes, init process, becomes the new ppid parent process ID. These processes are called orphan process. When a process is killed, a PS listing may still show the process with a Z state. This is a zombie process. The process is dead and not being used. These processes are different from orphan processes. They are the processes that have completed execution but still have an entry in the process table. Daemon processes. Daemons are system-related background processes that often run with the permissions of root and services requests from other processes. More clearly, a daemon is just a process that runs in the background, usually waiting for something to happen that it is capable of working with, like a printer daemon is waiting for printer commands. The top command is the traditional way to view your system's resources usage and see the processes that are taking up the most system resources. Top displays a list of processes with the one using the most CPU at the top. The ps command lists running processes. The ps-tree command is another way of visualizing processes. It displays them in tree format. So, for example, your X server and graphical environment would appear under the display manager that spawned them. The kill command can kill a process given its process ID. You can get this information from the PSA, top, or pgrep commands. Unlike traditional PS operating systems, Unix-related systems use very sophisticated memory management algorithms to make efficient use of memory resources. This makes the questions "how much memory do I have" and "how much memory is being used" rather complicated to answer. First, you must realize that there are 3 different kinds of memory, 3 different ways they can be used by the operating system, and 3 different ways they can be used by processes. Kinds of memory. Main, the physical random access memory located on the CPU motherboard that most people think of when they talk about RAM, also called real memory. This does not include processor caches, video memory, or other peripheral memory. File system. Disk memory accessible via path names. This does not include raw devices, tape drives, swap space, or other storage not addressable via normal path names. It does include all network file systems. Swap space. Disk memory used to hold data that is not in real or file system memory. Swap space is most efficient when it is on a separate disk or partition, but sometimes it is just a large file in the file system. OS memory uses. Kernel, the operating system's own semi-private memory space. This is always in main memory. Cache, main memory that is used to hold elements of the file system and other I/O operations. Not to be confused with the CPU cache or disk drive cache, which are not part of the main memory. Virtual, the total addressable memory space of all processes running on the given machine. The physical location of such data may be spread among any of the 3 kinds of memory. Process memory uses. Data. Memory allocated and used by the program, usually via malloc, new, or similar runtime calls. Stack, the program's execution stack managed by the OS. Mapped, file contexts addressable within the process memory space. The amount of memory available for processes is at least main plus swap minus kernel and may also include any files via mapping. Memory is one of the most important parts of Unix system for performance. Let's look at some commands that will tell you what you need to know about how your memory is being used. These commands will be useful during non-functional testing like performance, load, and stress. Free. One of the most basic memory commands available in Linux systems is the free command. Free will report memory usage in kilobytes if you don't tell it otherwise. The command below uses the M option to convert this to megabytes, a little easier a format for user to deal with. Meminfo. Looking at the meminfo file, we can see how much memory is installed as well as how much is free. To make your display a little more interesting and add measurements for swap, run a command like this: $egrep, color quotes mem pipe cache pipe swap quotes /proc/meminfo. In this command, we're using egrep to pull out any lines that have one of the 3 strings, mem, cache, or swap, within them. We have already mentioned this command when we were talking about process management. Let's see what we can find by using top command to get some information about memory. It can tell us so much about how a system is performing and in a format that is easy to digest. In this top output, we see the memory stats in rows 4 and 5. The total installed memory, along with how much is in use and free, are clearly labeled. Most Unix memory commands are fairly easy to use and understand, and frequent use will give you a feel for how your systems perform under normal circumstances and prepare you to notice when your system is in trouble. In Unix, there are 3 basic types of files. Ordinary files. An ordinary file is a file on the system that contains data, text, or program instructions, used to store your information, such as some text you have written or an image you have drawn. This is the type of file that you usually work with. Always located within under a directory file. Do not contain other files. Directories. Directories store both special and ordinary files. For users familiar with Windows, Unix directories are equivalent to folders. Branching points in the hierarchical tree, used to organize groups of files, may contain ordinary files, special files, or other directories. All files are descendants of the root directory named root, located at the top of the tree. Special files. Some special files provide access to hardware such as hard drives, CD-ROM drives, modems, and Ethernet adapters. Other special files are similar to alias or shortcuts and enable you to access a single file using different names. Unix uses a hierarchical file system structure, much like an upside-down tree with a root, / at the base of the file system and all other directories spreading from there. The root contains the entire file system. The directories have specific purposes and generally hold the same type of information for easily locating files. Following are the directories that exist on the major versions of Unix. / This is the root directory, which should contain only the directories needed at the top level of the file structure. /bin. Here the executable files are located. These files are available to all users. /dev. These are device drivers. /etc. System configuration files, startup and shutdown procedures. /lib. Contains shared library files and sometimes other kernel-related files. /boot. Contains files for booting the system. /home. Contains the home directory for users and other accounts. /mnt. Used to mount other temporary file systems such as CD-ROMs and floppy for the CD-ROM drive and floppy diskette drive, respectively. /proc. Contains all processes marked as a file by process number or other information that is dynamic to the system. /tmp. Holds temporary files used between system boots. /usr. Used for miscellaneous purposes and can be used by many users. Includes administrative commands, shared files, library files, and others. /var. Typically contains variable length files such as log and print files and any other type of file that may contain a variable amount of data. /sbin. Contains binary executable files usually for system administration, for example fdisk and ifconfig utilities. /kernel contains kernel files. Let's consider the main commands for the file management. To list the files and directories stored in the current directory, use the following command, ls. You can use the VI editor to create or edit ordinary files in any Unix system. To see the content of a file, you can use the cat command. To make a copy of a file, use the cp command. To change the name of a file, use the mv command. mv command will move the existing file completely into a new file. To delete an existing file, use the rm command. A shell is an environment in which we can run our commands, programs, and shell scripts. The shell provides you with an interface to the Unix system. It gathers input from you and executes programs based on that input. When a program finishes executing, it displays the program's output. The prompt $, which is called command prompt, is issued by the shell. While the prompt is displayed, you can type a command. The shell reads your input after you press enter. It determines the command you want executed by looking at the first word of your input. In Unix, there are two major types of shells. The Bourne shell. If you are using a Bourne-type shell, the default prompt is the $ character. The C shell. If you are using a C-type shell, the default prompt is the person character. There are various subcategories for Bourne shell and C-type shells. Thank you for your attention. Good luck with the next module.